In this video, we're going to cover the approximate method for trusses using method 1. Method 1 assumes that slender members cannot support compression, and that slender members do actually exist in our truss. So slender members are kind of similar to a cable, if you want to think of it that way. Cables can be put in tension, but cables kind of can't resist a compression force. If you try and compress a cable, it literally just becomes limp. So it really can't hold any compressive force in the slightest. And that's effectively what a slender member is. So for this truss, it's very similar to the one that we did in class. It's a box truss. We have the nice X diagonals there. So we have 10 kips going down at every single one of those top joints, E, F, G, and H, and we have a 5 kip force at joint E. Now we want to only find the forces at joint E. The rest of this is just a method of joints type problem, and it's a bit ridiculous to do the whole thing all at once. But let's start off by trying to identify our zero force members. Now, in order to identify them, again, we're looking for members that are in compression if we can, and remember that only the diagonals are slender, so really we're just looking for which diagonal members do we think would be in compression. So every single one of those top joints has a compressive force on the truss, but the big thing that we need to note is that only joints A and joints D actually have support, so B and C can deflect, right? B and C can move down. So that's allowing those joints there, those members, EC and HB here, even though they're being pressed on vertically down, they can still kind of scooch downward at B and C. So those members could potentially hold a force. They can be in tension. However, with AG, if you squish member AG down even just a little bit, right? If you were to squish this member down, say only that much, this member now just got shortened because he can't scoot at A. So he is a zero force member. And the same thing's going on over here at FD. At FD, again, if F were to scoot down just a little bit here, then our member would be a little bit shorter, which means he's in compression. So again, FD is also a zero force member. Now, when you come look at the middle box, you might be thinking, oh, well, I mean, if they can both scooch down, technically they could both be in tension, technically, but the whole box is shifting down, but it's also important to notice that we do have a little tension force over here, kind of pulling our truss. So FB is kind of being pulled a little bit further, maybe this way. And GC is kind of getting squished, right? If G kind of scoots over here, then this member, that member just got shorter. So technically, GC here is also a zero force member. I wouldn't really worry about the middle box. Again, you can probably discover all that if you're going through the entire method of joints. But that is the kind of mindset that we're going through. So that's where we're going to start with our zero force members. And again, we only want to find the forces at joint E. We don't need to do this entire truss. So what we're going to do is we're just going to take a cut here so that we can isolate it. And before we do that, we probably want to find the forces here at D. So this would be dy. So if I want to find dy, I'm probably going to sum the moments about A, right, since he's the only unknown in that case. So sum the moments at A, taking counterclockwise to be positive, setting it equal to 0. So our first load here, he acts in line with joint A, so he's not actually going to apply because his distance would be 0. So our second one, our 10 kip over here, he's going to be going that direction around A, so that's going to be negative. So we're going to have negative 10 times his distance of 20 feet. Our second one over at F, again, same thing, -10, but a distance of 40 feet. And then our third one at E, we have again -10, but a distance of 60 feet. That's a lot. Then we have E, and E is going to be going again that direction for that horizontal one at E. So again, negative. So we have -5 times a distance vertically here of 20 feet. And then lastly, we have dy. dy thankfully going in the positive direction, the one and only. So we have plus dy and his distance of 60 feet. So we're going to find that dy is equal to 21.7 kips. Keeping our 3 sig figs here. So now that we have dy, let's go ahead and break our little free body diagram out. So we have our vertical member. We have dy we just found, right? So dy is acting down here. dy, this was 21.7 kips. Then we've also got our loads, right? Up at the top, we got our 5 kip horizontal, and we've got our 10 kip going down, our vertical there. We have our angled members, and we have our horizontal members. So whereas we don't actually need the forces down at D, we might as well solve for them while we're here. So what do we got? We've got horizontally, this is force CD. Diagonally here, even though we did say he was 0, right? This is force F or DF. Again, he is 0. Just go ahead and mark him there. Then diagonally we have FCE. And then we have FCF. That's EF. FEF. Alrighty, technically in here, we also want to find this guy that we can't see, but this is FDE. Or going the other way again, right? This is FDE. So he's technically there, he's just not cut into the member. So to start with, let's just start analyzing joint D. So for joint D, we're gonna break him out. We have our vertical, our horizontal, and that diagonal, even though that diagonal is 0. Yay. Then we also have a vertical, 21.7. Our vertical force here, FDE, and then our horizontal, FCD. So if you sum the forces in the x direction, we have only one force, and that's FCD. So FCD is, he's also 0. So that makes that fun. And of course, the reason we're starting at joint D is because we do actually want DE, right? We did actually want to find him. So now if you simply sum the forces in the y direction, you get 21.7 plus FDE equals 0. So FDE is equal to -21.7 kips. Now, because he's not a diagonal, he can't hold that compressive force. So he is one of our answers that we wanted to find. And now all we got to do is go to joint E and check him out. So joint E, he's kind of looking the same way. Got a horizontal, got a vertical, got the diagonal. We have a vertical force of 10 kips. We have a horizontal force of 5 kips. We just found that FDE, I'm going to draw him in tension, even though we found he was -21.7 kips. Okay, we do want to actually keep note of him. Then we want to find FCE, and this guy at the top, this is FEF. So I have 2 unknowns horizontally. I only have 1 unknown vertically. So we're going to go ahead and sum the forces in the vertical direction, set it equal to 0. We got 10 going down, and we also, according to our arrows, also have our negative 21.7 going down. So technically he'd be going up, so our negatives are going to cancel out there. We also have our FCE force going down. And again, if we're looking back at our beautiful picture, it's 20 feet, 20 feet for horizontal and vertical. So for our triangle, that's going to give us 20, 20, and 20 square root of 2. I love that guy. So technically his component is 20 over 20 square root of 2 for the vertical component. So what we're going to get is FCE is equal to 16.5 kips. If you found that he was negative, I would either suggest to check your signs or to recheck whether this guy is actually a zero force member or not, because remember, he cannot hold compressive forces. So if you found a compressive force for a diagonal, you definitely messed up somewhere, or he is actually a zero force member in this case. So now that we have him, we can simply sum the forces in the x direction and set it equal to 0. We have a 5 kip force positive. We have minus FEF. And we also technically, by this arrow, minus the horizontal component, 20 over 20 square root of 2 of FCE. So what we're going to find is that FEF is equal to negative 6.67 kips, which again, it's okay, he's negative because he is not a diagonal. So for joint E, finding all those forces, he really actually wasn't too terrible. But again, the biggest thing about this is finding which one of those slender members is actually in compression. Once you've done that, everything else is simple from there.